What is a rock? Let's start somewhere easy. Let's open up a dictionary. The Oxford English Dictionary's definition of a rock is a large rugged mass of hard mineral material or stone forming a cliff, crag, or other natural features on land or in the sea. Ah, that's it. I guess we could stop there, but I want to know more. What makes something a rock? Rocks must be composed of one or more minerals. Minerals are composed of one or more elements. Okay, let's break this down. We'll start with the elements. Elements are atoms, the smallest piece that we can split matter into, except for subatomic particles. Let's leave that to the physicists in another video. Examples of elements: silicon is an element, oxygen is an element, quartz is a mineral. Both silicon and oxygen are the elements that make up quartz, which is a mineral. Next is minerals. A mineral is a naturally occurring solid substance with a definite chemical composition and crystal structure. Examples of minerals: quartz, feldspar, biotite are all minerals that make up granite, which is a rock. And finally, the rock. Monomineralic rock. These rocks are primarily or entirely composed of a single mineral. Examples of monomineralic rock are quartzite, primarily composed of quartz; limestone, primarily composed of calcite. Polymineralic rocks. Most rocks are composed of multiple minerals, also known as polymineralic rocks. Examples of polymineralic rocks are granite, which is composed of quartz, feldspar, mica. Another example is coal, which is composed of quartz, clay minerals, pyrite, calcite, and siderite. We've gone over what makes up a rock, but I'd like to know, what are the different types of rocks? Rocks are commonly divided into three major classes according to the processes that resulted in their formation. There's igneous, sedimentary, and metamorphic rock. Igneous rock. Deep in the Earth's crust, there are places where the rock is melted into magma, which is a mixture of crystals and liquid rock. Sometimes the magma erupts out of the earth through a volcano, and then it is called lava. Formed when the lava cools and hardens on the Earth's surface, it is called volcanic igneous rock. If the magma cools and hardens under the ground, it is called plutonic igneous rock. This rock is very hard and has no layers. Examples of igneous rock are granite, which is intrusive, slow magma cooling, and obsidian, which is extrusive, which is rapid magma cooling. Sedimentary. Formed through accumulation, compaction, and sedimentation of many sediments over a very long period of time. Fragments of rocks and minerals that have been eroded from pre-existing rocks and put into different environments, such as bodies of water. Throughout millions of years, the sediments go through lithofaction, which is the process of sediments undergoing pressure, which turns them into solid sedimentary rocks. They form from sediment compaction and are characterized by their crumbly and layered structure. Examples of sedimentary rock are sandstone, which is clastic, formed from compacted broken rock fragments; limestone, which is chemical, formed from dissolved minerals that settle and harden over time; coal, which is organic, formed from compacted biogenic matter. And I guess it's okay to call coal a rock. Metamorphic. Just like cookie dough changes as it bakes, rocks change when they're heated, squeezed, or both. Rocks deep within the earth are put through intense heat and pressure. In time, these forces change sedimentary or igneous rock into another type of rock called metamorphic rock. They are formed by the transformation of other rocks. They are relatively hard and may or may not have layers. Examples of metamorphic rock are slate, which is foliated and has layers; marble, non-foliated. It has no layers. Great, so now you know what makes up a rock and the different types of rock. You ask yourself, why do rocks exist? The Big Bang is the most accepted theory for the origin of the universe. The universe started from an extremely small and dense point, otherwise known as a singularity. The singularity rapidly expanded and continued to stretch over 14.5 billion years. This initial period of rapid inflation set the stage for the vast universe. To this day, it is still expanding. The only elements created at the beginning of our universe are hydrogen, helium, and lithium, the three lightest atoms in the periodic table. If we remember and look back, rocks are made out of minerals, which are made from elements. Rocks could not have formed with the existence of just the primordial elements. The heavier elements that are in the minerals that make up rocks were not created in the Big Bang, but rather much later in the life or death of stars. If we look at how silicon and oxygen were formed, it was formed in a dying high-mass star. The dying high-mass star resulted in a supernova, which is the colossal explosion of a star. Gas and dust are ejected into space, coming together to form a massive cloud, a structure known as a nebula. The solar system's formation began with a nebula, rich in heavier elements like silicon and oxygen, the results of a supernova that seeded space with the building blocks of rocks. These elements are found in quartz, a mineral that helps make up granite. Also, this periodic table shows how elements were formed in the universe is so cool. I totally geeked out when I found it. Key points about the formation of the first rocks. Our solar system, including the first rocks, originated from a rotating cloud of gas and dust called the solar nebula. Within this nebula, tiny particles of dust and debris in space gradually stuck together, forming larger objects called planetesimals, which eventually collided and combined to create the Earth. Today, we can study the oldest rocks in our solar system through meteorites, which are remnants from the early formation of planets. I guess they come from the Big Bang, but I thought I was just learning about rocks from here on Earth. What about this one? The first rocks on Earth were formed from the cooling and solidifying of molten material called magma, which was present during the early stages of the planet's formation. It eventually cooled and crystallized into the first rocks, with the oldest known rocks being igneous in nature and dating back nearly 4 billion years. As the Earth began to cool, the molten magma solidified, forming the first igneous rock. Some of the oldest rocks known on Earth are found in places like the Castanese complex in Canada, which is pictured in shades of red. The Castanese complex is a formation of Archean rocks located in the Slave Craton of the Canadian Shield in the Northwest Territories of Canada. The Canadian Shield is a broad region of Precambrian rock. It's considered the oldest known intact piece of the Earth's crust, containing rocks dated to 4.03 billion years old. The formation is found near the Acasta River, about 300 kilometers north of Yellowknife. So Big Bang, solar nebula, accretion, magma, igneous rock. Igneous rock. I understood that one. Now these rocks are down to earth. How are rocks formed? The rock cycle reflects the basic relationships, as previously explained, among igneous, metamorphic, and sedimentary rocks. Let's start with the fundamental principle of science, known as the law of conservation of mass. Matter can change from physical and chemical changes, but through any of these changes, matter is conserved. The same amount of matter exists before and after the change. In summary, matter cannot be created nor destroyed. Since matter, or in our case rocks, cannot be created nor destroyed, how are rocks formed? Rocks are formed from older rocks. Other rocks are either broken apart, melted, or transformed. The process of the formation of new rocks from old rocks is known as the rock cycle. Let's dive into this a bit more. We'll start with the 3 rock types we've previously discussed: igneous, sedimentary, metamorphic. We'll also add sediments that represent rocks that have been broken down, as well as magma to represent rocks that have been melted. Igneous rocks. Rocks that are exposed to extreme heat are melted into magma. All 3 rock types, even igneous rock, can undergo melting. Extreme heat is represented by the red lines. Once magma and lava cools, igneous rocks are then formed. Cooling is represented by the blue line. Sedimentary rocks. Rocks that are exposed to weathering, erosion, and deposition are broken down into sediments, otherwise known as denudation. All three rock types, even sedimentary rock, can undergo denudation. Denudation is represented by the dashed black lines. Once sediments undergo deposition, cementation, and compaction, sedimentary rocks are formed. This is also known as lithofaction. Lithofaction is represented by the pink dotted lines. Metamorphic rocks. Rocks that are exposed to heat and pressure are then transformed into metamorphic rock, a process known as metamorphism. All three rock types, even metamorphic rock, can undergo metamorphism, which is represented by the green zigzag lines. This represents the rock cycle. This is how igneous, sedimentary, and metamorphic rocks are formed. Great, now I understand how rocks are formed. Who can I thank this for? James Hutton is attributed to the creation of the rock cycle and considered the father of geology. James Hutton, 1726 to 1797. Hutton recognized that geological processes have no sign of a beginning and no prospect of an end. The processes involved in the rock cycle often take place over millions of years. On the scale of a human lifetime, rocks appear to be, rock solid and unchanging. But in the longer term, change is always taking place. He also introduced the concept of uniformitarianism, the idea that geological processes like erosion, sedimentation, and volcanic activity have operated in similar ways and at similar rates throughout Earth's history, both past and present. Hutton argued that the Earth's features, like mountains and valleys, were formed not by sudden catastrophic events, but by the slow, continuous accumulation of these natural processes over immense timescales. His publication, Theory of the Earth, provided a comprehensive framework for understanding the Earth's history and processes. No wonder he was known as the father of geology. He's a rock dad. This dad rocks. Hutton never found fame during his life, but his portrait of an ever-changing planet had profound effect. Well, that sucks. At least we were able to learn about him. I guess I learned a few things about rocks, but I still kind of have some of those dumb questions I want answered. I really want to know more about rocks. Do rocks cause earthquakes? First, let's go over a couple of things. The Earth's crust is broken into large, moving sections called tectonic plates. Beneath the crust lies the mantle, where convection currents drive the tectonic plates. The tectonic plates' movement. They shift like sheets of ice gliding over the mantle, moving only a few inches each year. The edges where these plates meet are called plate boundaries. They move away, towards, and past each other. Plates that move towards each other are convergent boundaries. There are 3 types of convergent boundaries. Let's start with continental to continental. This occurs when 2 continental plates run into each other. As the plates run into each other, the plates thicken and create mountains. The collision of the India plate and the Eurasian plate forming the Himalayan mountains is a prime example of this. Continental to oceanic. This occurs when a continental and oceanic plate run into each other. As the plates converge, the oceanic plate subducts under the continental plate. This is because the oceanic plates are denser than the continental plates. Oceanic plates are composed primarily of basalt rock, while continental plates are primarily composed of granite, which is less dense. As the ocean plate subducts, it melts and magma begins to rise, which causes the formation of volcanoes. The formation of the Andean volcanic belt is a prime example of this. Oceanic to oceanic. This occurs when 2 oceanic plates run into each other. the plate that is older and more dense will subduct under the younger plate. Because of this, the crust melts and creates island arc volcanoes. An example of this is the Pacific Plate and North American Plate converging. As a result, the Aleutian Islands of Alaska are formed from this. Those are 3 different types of convergent boundaries. Convergent boundaries are home to reverse faults. The next type of boundaries are divergent plate boundaries, which means plates move away from each other as a result. This allows the asthenosphere to rise up. Lava then begins to erupt to form a new oceanic and continental crust, which is part of the lithosphere. An example of this is the North American Plate and the Eurasian Plate diverging from each other. A classic case of ocean-to-ocean divergent boundary is seen at the Mid-Atlantic Ridge. It's really neat to see this underwater structure of the 2 ocean plates separating. I always wondered what those mountains were in the ocean on the maps of the Earth, and now it makes sense. Cool. There's also divergent continental-to-continental plate boundaries. An example of this is the North American Plate and Eurasian Plate diverging from each other, creating Iceland. This is the reason why Iceland is so volcanically active. Divergent boundaries are home to normal faults. And finally, there is transform boundaries. This is when 2 plates move past each other. The movement does not create nor destroy crust as 2 plates slide past each other. There's a lot of friction and scraping. Tension builds up along the fault line. The slippage of the movement releases a tremendous amount of energy. This is generally where most earthquakes occur. An example of this is seen at the San Andreas Fault. Transform boundaries are home to strike-slip faults. Faults allow the blocks to move relative to each other. This movement may occur rapidly in the form of an earthquake. An earthquake is what happens when 2 blocks of the Earth suddenly slip past one another. The surface where they slip is called the fault or fault plane. The location below the Earth's surface where an earthquake starts is called the hypocenter, and the location directly above it on the surface of the Earth is called the epicenter. Let's look at an example. 2 plates shear past each other, like the recent quake in Southeast Asia. They may not release as much energy as the reverse faults, but can be more destructive because they are closer to the surface. Data suggests that the Myanmar earthquake was caused by this. The Sagang Fault, which cuts right through Myanmar north to south and is more than 1,200 kilometers long. Okay, so that's how earthquakes are formed. Where do earthquakes occur? Earthquakes primarily occur in the crust and upper mantle, specifically within the lithosphere, where tectonic plates interact and move. Lithosphere. The Earth's lithosphere, which includes the crust and upper mantle, is made up of a series of pieces, or tectonic plates that move slowly over time. This is a rock. So in turn, rocks do cause earthquakes. Okay, yeah, I think this makes sense. Basically, earthquakes occur on the crust, which is above the mantle. Crust or lithosphere is considered rock. The difference between rock and stone. According to Oxford's Learner's Dictionary, it defines stone as a hard, solid mineral substance that is found in the ground, often used for building. That's pretty broad. Let's look more into this. At what size does a pebble become a rock? When does a rock become a boulder? Is there any reliable metric for distinguishing between them? Rock is a material. It is not a size. A pebble is a rock. A boulder is a rock. Usually, we keep calling particles of natural stone rock until the size of particles gets really small. For instance, sand-sized materials is the size right below pebbles. This is all very complicated. Do people actually study or need to use this information? It's a bit ridiculous to need to know the size of a grain of sand. As for a reliable metric, yes, of course. Geologists and soil engineers and civil engineers standardize size ranges for rocks. They don't usually use the word pebbles to describe a defined size, but if they did, they would include fine gravel to medium-sized gravel sizes. Granulometry. Granulometry is the measurement of the size distribution in a collection of grains. It is often characterized by the percentage of particles with certain diameter ranges. What are the smallest rocks? Clay is 0.002 millimeters, which is the boundary for mineral analysis. Fine silt, which is 0.002 millimeters to 0.0063 millimeters. The biggest rocks, which are large boulders, are greater than or equal to 630 millimeters. Let's look into other rock structures. Monoliths, the largest in the world. Uluru, also known as Ayers Rock, is a massive sandstone formation in the Northern Territory of Australia. It measures at 1,142 feet tall, 2.2 miles long, and 1.5 miles wide. Here's the top 10 of monoliths. Uluru, Benamera, El Capitan, Peña de Bernal, Devil's Tower, Siguria, El Peñón de Guatape, Zuma Rock, Rock of Gibraltar, Sugarloaf Mountain. Is the lithosphere considered rock? Lithosphere, which are seismic plates that go from 50,000 meters to 200,000 meters deep, which are solid slabs of rigid rock on the outermost layer of Earth. It's made of solid rock and minerals. Is it a rock? Let's go back to the beginning and remember what are the things that make rock. It has to be naturally occurring, solid, inorganic, and made up of one or more minerals. Let's see if we can get any of these right. Magma. Magma isn't a rock because it is a semi-molten mixture of rock, minerals, dissolved gases, and solid pieces found beneath the Earth's surface. Minerals. No. A mineral is a naturally occurring inorganic solid with a specific chemical composition and crystal structure. A mineral can be called a rock, but a rock cannot be called a mineral. Charcoal. No. Charcoal is a man-made product. You can make charcoal by heating wood to high temperatures in the absence of oxygen. Asphalt. No. Asphalt is a composite material, meaning it's made up of multiple components. It primarily consists of aggregates, crushed stone, gravel, and sand. Bitumen is a sticky, black, petroleum-based substance. Asphalt is a man-made product. Ice. Yes and no. Definition of a mineral: a naturally occurring and inorganic solid with a definite chemical composition and regular crystalline structure. Ice fits this description. Here's how we can classify the different types of ice rocks. Snow can be considered sedimentary rock. Ice formed on lakes can be considered igneous rock. Glacier ice, metamorphic rock. Ice in the freezer, not naturally occurring. The ice in your freezer does not count as a rock. Diamond, no. Diamond is a crystal of pure carbon. Bonus question: if a diamond is not a rock, why can't it be classified as a monomineralic rock? Comment your responses. The best response wins this book. Well, about rocks. Mysterious rocks. The mystery of the sailing stones. In one of the most desolate corners of Death Valley National Park lies a captivating mystery. The sailing stones of Racetrack Playa. These rocks, some weighing hundreds of pounds, leave eerie trails etched into the desert floor, appearing to move entirely on their own. For decades, their unexplained movements baffled scientists and inspired countless theories and myths. Some of the theories were high winds, magnetic fields, animal intervention, human pranksters, and even alien intervention. These theories would be put to bed as scientists were finally able to uncover the secret behind the sailing stones. First, GPS trackers were attached to several stones. Next, time-lapse cameras were positioned around the Racetrack Playa. Then, the scientists needed to wait for just the right environmental conditions. On cold winter nights, a thin sheet of ice formed across the playa, encasing the stones. As morning came and the sun began to rise, the thin ice panels began melting and cracking apart. Light winds pushed these ice panels, which nudged the stones, causing them to glide across the slick, wet surface. This phenomenon was documented during the winter of 2013 to 2014, finally ending decades of speculation. The findings are attributed to Richard Norris, James Norris, and their collaborative team. Their findings not only solved a long-standing geological puzzle, but highlighted the intricate interplay between environmental conditions and natural phenomena. Religion and rocks. Dome of the Rock, the foundation stone. The stone is located in Jerusalem, Israel. Inside the Dome of the Rock, the foundation stone sits at the center. The rock is also known as the pierced stone, due to the small hole in the southeastern corner, which leads to a cavern beneath the rock, known as the Well of Souls. The surrounding area is known by different names, depending on one's faith. In Judaism and Christianity, it is known as Temple Mount. To Muslims, it is known as the Noble Sanctuary. From a scientific perspective, the foundation stone is a part of a 90-million-year-old geological formation which dates back to the Upper Turonian stage of the Late Cretaceous period. Here's a description of the layering of the different stages and periods. Much of Jerusalem itself sits on the uppermost beds of the Judea group. Rocks deposited during the Turonian stage are known as Turonian rocks. The foundation stone is believed to be composed of karstic limestone, which is a sedimentary rock. The foundation stone and the dome of the rock are powerful symbols of faith, which draws many pilgrims and visitors each year. The Black Stone. The Black Stone is a rock that is set to the eastern corner of the Kaaba, which is the ancient building that sits at the center of the Grand Mosque in Mecca, Saudi Arabia. The Black Stone serves as a symbol of faith and devotion for Muslims around the world and draws millions of Muslims to Mecca each year. From a scientific perspective, the exact nature of the Black Stone still remains a mystery. While it is widely believed to be a meteorite or a mineral such as obsidian or agate, modern scientific analysis has never been conducted. Its precise geological origins remain speculative. OSIRIS-APEX. OSIRIS-REx was launched in 2016. The spacecraft initially targeted asteroid Bennu, with its goal to uncover the rocky mysteries of our solar system. Samples from Bennu were successfully returned to Earth in 2023. Renamed OSIRIS-APEX, this spacecraft now prepares for an encounter with the near-Earth asteroid Apophis, scheduled for April 8, 2029. Apophis is a near-Earth object at roughly 1,100 feet or 340 meters long. Apophis was once thought to have the chance of smashing into Earth in 2068, but is no longer considered a threat. Apophis will skim past Earth at a distance of 32,000 kilometers, closer than some satellites. OSIRIS-APEX will then carefully monitor the asteroid. OSIRIS-APEX will not be able to collect samples from Apophis, but will study the asteroid for 18 months. These proximity operations will include imaging and mapping the asteroid, as well as a close-up rendezvous maneuver. Apophis is classified as a rocky or S-type asteroid. Studying it closely could reveal new insights into a different class of asteroids. By comparing Apophis's data with Bennu's samples and data, OSIRIS-APEX will help refine our understanding of asteroid diversity, inform us on planetary defense strategies, and deepen insights into our own origins. The OSIRIS-APEX mission isn't just exploring a rocky S-type asteroid, it's exploring the fundamental questions about the history of our solar system and humanity's place within it. Consumption of rocks. Have you ever heard of people eating rocks? It might sound strange, but it does happen. This practice is sometimes called geophagy or lithophagy, which is the practice of ingesting stones. It's a behavior in some birds as well as some reptiles. But what about humans? In certain cultures, especially among pregnant women and children, people consume rocks. The rocks consumed are typically of the softer varieties like clay or chalk. In various regions of the world, the consumption of rocks is observed. In Europe and the United States, this behavior is considered a psychological disorder called pica, which is the craving and consumption of non-nutritive substances, including rocks. It is medically discouraged. But I'm sure you want to know, what do rocks taste like? Here are a few examples. According to the Museum of Edible Earth, in Nigeria, a clay known as salty kalaba is consumed. Its taste is described as having an uneven structure, being very snacky, having a nice salty taste, which is also creamy and sticky, but also crunchy at some parts. It's a naturally occurring material made of fossilized seashells. As with some edible clays in West Africa, it's commonly eaten by pregnant women. In France, green clay chunks is a popular edible clay. Its taste is described as having a deep, fat taste of swamp, with a sticky and grainy texture. It tends to stick to the tongue, and is used for external cosmetic treatments such as skin problems and internal applications such as digestive disorders. Apparently, it was sold as a food supplement in the past, but with new regulations, it has lost the status. In Suriname, rounded clay spheres known as pemba balls are consumed. Its taste is described as having a creamy, earthy, lightly smoked flavor with a fine grit infused with a hint of sour notes. It is also a naturally edible shape. Pemba is often eaten as a snack and is especially valued by pregnant women. But this special kind of edible clay is not merely a deeply rooted element of everyday life. On a spiritual level, it is an essential component of Winti religion. Those are just a few of the examples I was able to find. Would you ever try to eat rocks? I am curious to try now, but then again, no. Please do not eat rocks. Eating rocks can be dangerous. They can contain harmful substances like heavy metals, cause intestinal blockages, damage teeth, and lead to infections. Don't eat rocks. So it looks like we've been learning a lot of things about rocks. I never thought to ask this, but what is the study of rocks? Let's start off with geology, the parent discipline. Geology is the broad scientific discipline that is dedicated to the understanding of the Earth. It includes the study of the Earth's physical structure, history, processes, and its constituent materials, including rocks, minerals, and resources. Petrology is a specialized branch within geology. It focuses specifically on the rocks and the condition that formed them. Petrologists examine the composition, texture, structure, and origin of the three main rock types, which we know are igneous, sedimentary, and metamorphic rocks. A geologist can study earthquakes, groundwater, landforms, or the Earth's history without focusing in depth on the specific formation and composition of every rock type, which is the domain of petrologists. Petrology is the study of rocks. Well, that seems to encapsulate the study of rocks on Earth. What about the rocks not on Earth? Petrology traditionally focuses on Earth rocks, the study of rocks and rock-forming materials, from asteroids, meteors, and other bodies in space, which falls under a few specialized and overlapping fields. Planetary geology, which is the parent discipline. Planetary geology is the study of the geology of celestial bodies, such as planets and their moons, asteroids, comets, and meteorites. It applies geological principles to understand the formation, composition, and evolution of these extraterrestrial objects. So planetary geologists would study the rocks and geological processes on an asteroid or another planet. Meteoritics, which is the subdiscipline of planetary geology. This is a specialized branch that deals specifically with meteors, meteoroids, and meteorites. Meteoricists analyze meteorites to learn about the early solar system, the composition of asteroids and their parent bodies, in addition to the processes that occurred during their formation. Cosmochemistry. This field focuses on the chemical composition of matter in the universe. and the processes that led to those compositions. It heavily relies on the study of meteorite samples, as they are direct samples of other celestial bodies and preserve records of the early solar system's chemistry. Cosmochemists analyzed the elemental and isotopic composition of these space rocks. Well, that seems pretty interesting. I'd like to know, are there any differences between rocky objects in space? Asteroids. They are a physical object. An asteroid's composition can be three types. Seep-type carbonaceous are the most common. These are dark primitive asteroids rich in carbon compounds, clay, and silicate rocks. S-type stony. S-type stony asteroids can be composed mainly of rock silicate minerals such as olivine and pyroxene mixed with metallic nickel iron. These silicates are the same kind found in many rocks on Earth. M-type metallic. M-type metallic asteroids primarily consist of metallic nickel iron thought to be the cores of shattered planetesimals. As for its location, they orbit around the Sun and space. A lot of them are in the asteroid belt. Its orbit around the Sun is primarily circular and occurs within the solar system's plane. They can be rubble piles, solid, rocky, or metal, and generally does not have a lot of ice. Asteroids can range from 1 meter to hundreds of kilometers. Comets. Comets are physical objects. They are composed of primarily ice, dust, rock, and are generally looked at as a dirty snowball. Comets orbit the Sun and often originate from the Kuiper Belt or Oort cloud in space. Its orbit around the Sun is highly elliptical and can be at any inclination. When near the Sun, due to the heat from the Sun and the melting of the ice, which then vaporizes. While the size of the comet's nucleus can range from a few hundred meters to tens of kilometers, the coma or tail can be as long as millions of kilometers. Meteoroid. Meteoroids are a physical object. Meteoroids can be composed of rock, metal, or dusty icy debris from asteroids or comets. Orbits can be varied and often related to a parent body's orbit, such as the Sun, the planet, a moon, or even an asteroid. They are the small body in space which is the source of meteors. They are much smaller than asteroids. The size range can be anywhere from a single dust grain to 1 meter. Meteor. This is a light phenomenon and not a physical object. It is caused by a meteoroid, which can be rock, dust, and ice fragments, which burn up in the Earth's atmosphere. It is a streak of light and is also known as a shooting star. Its orbit is not applicable, but it did have one before entering the Earth's atmosphere. Meteorites are physical objects. They are composed of rock, metal, stony iron, which is a survived fragment of a meteoroid. They are found on the surface of Earth or other celestial bodies. It does not have an orbit as it has already landed. The size varies greatly from small fragments to very large masses. An example of this is the Hoba meteorite, which weighs about 60 tons. So the term meteorite refers to any natural extraterrestrial object that has made it to the ground, regardless of whether it was initially classified as a smaller meteoroid or a larger asteroid while it was in space. The key is that it has survived atmospheric entry and it has landed. Well, it seems like we've learned quite a bit about rocks. What they are, how they form, where they come from earthbound stones to interstellar rocks. But there's one question left. How long do rocks actually last? Earlier, we learned about the rock cycle, a never-ending transformation. Technically, rocks don't die, unless the sun expands into a red giant in about 5 billion years and swallows the Earth whole. That might do it. So much for Earth rocks. But what about rocks out there, across the universe? Remember the Big Bang Theory? The universe is still expanding. Eventually, it might collapse in the Big Crunch or stretch endlessly into the Big Rip. Either way, even atoms, the building blocks of rocks, won't survive forever.